The next speaker is Mr. Romaric Massard. He is from the company Elstar Dynamics in Netherlands. He has a PhD in chemistry and about 20 years of experience in optical switching devices. He's the founder and CTO of Elstar. And the title of this lecture is Energy Efficiency of Windows Integrating Electrophoretic Light Modulators. The floor is yours.
Thank you very much. Thanks for attending. Basically, so we are Elstar Dynamics. We have a booth on the step-up change. We are developing a new type of smart glass window. So this one you electrically wire. It's electrically driven. It's based on the electrophoretic effect, not on electrochromic or SPD or LCD as usually commonly known. It's regarding electrophoretic effect, which is also known in e-readers. You may have this type of technologies. That's the same physics. So it's already a proven type of physics. Where are the slides? Yeah, thank you very much. So basically, I invite you to come to the step change area because we have a real demo. So if you want to visualize them, they are smaller than the one on the picture. This one is a 1 meter by 60. It's currently our largest prototype. And basically, you have a view on the dark state and the clear state that we can modulate. The system function, like shown in the diagrams. So between the two glass plates, we have a set of metal electrodes, non-transparent metal electrodes that cover each surface. And when we apply an electric field across these electrodes, we have a liquid between the glass composed of pigments which absorbs the light and a transparent liquid solvent, like in the paint. And the pigment can be moved by the electric field. They agglomerate behind the electrode, so they hide behind the electrode. And the remaining liquid between the electrode is transparent, so the system becomes transparent. A real live video of our view of our office. We press the button and you're going to see within 1 or 2 seconds, I think we have put 1 or 2 second delay in the electronic board. And you see an immediate reaction of the system. We are extremely color neutral thanks to the fact that we put the color element behind the electrode. So even if we were starting with a red or a blue pigment, when we get to color, when we go to the full optical clear state, the system will remain color neutral. An overview of the performance we currently have. So the black line is the dark state spectra, and the green line is the clear state spectra. Basically, we absorb all the visible part and big part of the infrared. So all the energy is accumulated into the window when we are going to clear state. As we take the coloring material, the one that absorbs the energy behind a reflective metal, non-transparent, basically you get a full transmission of the spectra. We currently have a very strong range. We go from 0.2 to 70%. This is the video you have observed. On the booth, we can engineer the system differently, as we can modify the distance between the glass, the distance between the electrodes, the shape of the electrodes, the electrophoretic ink, which is also formulated by yourself, we can also modify it. So the one you have on the booth, they go from 0.06% to about 65, 66%. So a bit less transmittant, we have shifted the system. It all depends how we want to, depends on the project application we have behind. So the one I showed on the video, they were having about 25% coverage of metal on the glass surface, which limit the maximum transmission range. The one on the booth, they're around 35%. But all of this could have implication not only on the transmission, but also how the energy is managed. As mentioned, we operate immediately, and within few minutes, you get a full swing operations. The power consumption, we are about 0.5 watt per square meter for the maximum power requirement. So for going from the dark state to the clear state, for every intermediate grayscaling, that will be intermediate power consumption. We put the system with a maximum peak voltage at 24 volts to be sure we can be automotive accepted and not going too high in power. And currently operation, we are testing between minus 20 degrees and 90s. Depending on project, sometimes we explore a higher range, but that's at the moment what we fulfill. So I forgot to mention at the beginning, I'm very loosey on this one. This presentation is showing the work we've done together with Eckersley O'Callaghan on the energy modulation. So basically, we provide the data to EOC, and the engineers perform an agreed modeling to see how much the energy efficiency. So Elstar didn't run this study in a way. So it's a trusted third party who did that. So the first question was to get to a few cities and see how our system can modulate properly. So the first question was, what is the right area for the cities according to them between the transmission, the visible transmission you want to have to the window and the G-value modulation? And we come up with these graphics where basically it shows between the dark and the clear state how the window will be accommodated. This is for commercial application. Maybe I should phrase this, it will be flagged later. So basically the idea is to start with our current dark state, in average 0.1%, and with the transmission range, what is accommodated with the G-value. And when we integrated our spectral data, and honestly speaking, this is the data which are not necessarily dedicated to that case study. So we pick up our regular demonstrators, we measure them on the UV spectrophotometer, also by a third party called OMT. They are in Eindhoven as well. We are based in Eindhoven, in Netherlands. So it's quite convenient. And basically we transfer those spectral data, and this is the outcome. So what you can observe is the red line is just our modulator out of the production, just the thin two glass together with the ink in between. And this one, as it absorbs all the energy, also behave as a black body. He radiates back the heat that he absorbs at some point. So that's why when you get the dark state G value, you're still pretty high, because you need to integrate that into a window construction to keep rejecting the radiated infrared values. So we start with the red lines, and by combining with different conditions, so first laminate, it doesn't change much the area of performance, but we start developing a system that is described here, different double glazing unit system. This is purely theoretical evaluation at this stage. Basically, we can shift the performance towards the window of application, where basically we are within the acceptable area, especially for Amsterdam climate. Again, this work theoretically doesn't consider any change in our current modulator, and we can engineer the modulator to modify a lot of things to adapt better. So we find out that Amsterdam was better fitting with the demonstrator that we have measured. Then we establish a model condition. So we did a shoebox model, simple one, commercial use. So limited, so with a standard room, also according to pre-existing literature study from other technologies, we also have a comparison point. And we have a 12 square meter window area. It's a commercial case study, so we only work during weekdays to operate the system. So at night, the system doesn't operate. So when we don't operate the system, it becomes black. Same over the weekend. So during 8 in the morning to 6 p.m., the windows will be modulating. And you have a number of settings, all the conditions of the testings are referred here, how we consider the criteria for manipulating the energy in the room. And what's important is the KPIs we considered. So we consider the energy, of course, how much energy we will save from cooling and heating for the room. The annual solar exposure. So one of the points, we wanted to have something which is realistic. So if you have a window that can go black to 0.1%, in some cases in summer when your daylight is very, very strong, yes, you will be at this range of transparency because you still see through very well into your room. But the idea was not to fake the model and to still have a minimum of natural daylight coming into the room. Otherwise, you just plug, to save energy, you just shut down your system and you just switch on the light. But the idea, it's not what people are going to do. People want natural light, and that's the idea of dynamic glass. So we put a criteria to have a maximum to have the annual solar exposure for the maximum light allowed in the room, and a spatial daylight autonomy to have a minimum amount of light natural getting into the room. Yes. And basically, that's the outcome that we focus on Amsterdam, because that was the one giving the best fitting for the window. We had to modify our modulator, as I explained, and then remeasure them if we want to look at the other cities. And basically, what we find out is, depending on the exposure, and the system has been optimized for the south window exposure, we replicate the same conditions for the other orientations. That's why the most energy efficiency is done on the source exposure. But basically, if we compare the baseline, which is already a double glazing unit system, to the one with the two construction we put with our electrophoretic light modulator, we have significant gain within a realistic commercial application, where we leave natural daylight still coming into the room. So. And that's about to conclude. Basically, source orientation is necessarily always the one where you get the best benefit, but every orientation has benefits, and we can save energy significantly already in Amsterdam, and this work will be followed up in future with the targeted product application we are currently constructing, where this will be fitting further. And we will see with territory how to modulate the system. Yeah, and that's the end. Thank you very much.